Sure. Um, yeah, have you been, I guess obviously you've been thinking about it. Have you been leaning towards any direction or? Nice. Yeah, yeah, yeah. Have you heard anything from them? Like about what they're doing? Okay, because I have. Um, yeah, because I'm enrolled in like I'm doing the Masters of Math for Teachers right now because I'm upgrading my master's degree. So I'm actually a student at U of Waterloo right now, but online. But I still get all the emails, so I can forward you some of the emails um, that they've been giving me just about what they're planning on doing next year. So yeah, I got one today actually. That's my latest email. I got it an hour ago. Subject: Your health and wellness during COVID-19. So yeah, there's lots of information that they're giving out. Um, I think the way they're doing it is that they're still going to have classes. They don't know what the situation is going to be. So I think the idea is that if things are okay, then they'll have classes. But my guess is that's very unlikely. So they would probably just have distance learning. So I don't know what that would look like, but I can. They sent me an email about a month, not a month ago, maybe a week ago. I've completely lost track of time, but they sent me an email a while ago that kind of outlined their procedure, and I kind of dismissed it because it didn't really apply to me. But I'll find it and I'll send it your way. Um, yeah, that's was it 9 billion for students? I don't know how much. Like I don't know how many students there are, so maybe that's like $50. But oh, nice! Wow, cool. Nice. That's perfect. That's perfect. So that's from like that's for the whole year. Okay, that's great. That's perfect. Yeah, that would definitely be a boost. Cool. Yeah, yeah. It sucks, but I mean, rather be here than other countries. Um, yeah. Okay. Well, it looks like it's just the three of us. I'll send a message to everyone. AP Calc. True. A lot of doors closing. Yeah. Maybe two or three new doors are opening, but yeah. Okie dokie. Mm-hmm. Mm-hmm. Yeah. Yeah. I mean, you could still go there, right? Like you could still move there and then do distance learning, and who knows, maybe your first semester would be distance learning, and then after that, maybe they would open the schools, and then you'd be there, and you could just like walk down the street and come to school rather than staying at home all all the time, right? Mm-hmm. Yeah, yeah, that could be pretty isolating. Yeah, that's a good point. Yeah, yeah. Um, mhm. Are you? Is anyone else thinking of going to Waterloo? Is that in the cards for anyone else? No. There you go. I mean, it's similar university. Yeah. Yeah. I think it takes... Yeah, it's true. Oh. Yeah. I mean, you'd be surprised. You meet a lot of people, but I mean, actually, I don't know if that would be the case next year, right? Maybe you wouldn't meet anyone because you'd be holed up in your apartment. But yeah, yeah. I mean, that can happen anywhere you go, right? Like you can stay in Winnipeg and then you can have a bad experience with your roommate not even going to school, right? So there's always going to be a risk for that kind of stuff. Why would you hope that? Hmm. Yeah. Are you? Yeah, I think we all are. I don't know. I wonder how much longer we have. 6 months? 8 months? At least May 20th. I'm Yeah, something tells me we'll be inside for a long time. But I don't know. Maybe not. We'll see. Um, just gotta stay safe. Gotta stay safe. Yeah, I heard you can transmit it over video conference. It's sometimes known as a computer virus. Um, okay, let's get started. I think we should do some examples. So do you guys want me to do an example to start, or do you want to try an example yourself and then like evaluate it after the fact? What do we think? Do you like okay? So what I'm asking is, should I start off with an example and just do like a fully worked example and then give you an example, or do you guys want to hit the ground running? I give you a question, you see what you can do, and then we kind of take it from there. Okay, so we got one person doing option one. I think I saw a two in a different frame. Anyone else have an opinion? No? I'm okay. Okay. Why don't I do an example then? I'll start off with an example, and then you guys actually have to try some examples. Like I'm thinking today's like if we were in the classroom, I would call today a work period. We're gonna be doing some work, so I want to see some pencils out and paper. So we're not gonna be, hey, there we go. I see some paper. That's good. So yeah, I want to make sure that we're actually doing some practice here. So let's try. I think I was looking at this example here. Let's see here. Yeah, okay. I think we should do this example. Oh, is that a cat? Do I see a cat? Oh, nice. Oh my gosh. My cat looks just like that. Here, let me get my cat. We'll do a little cat conference. Yeah, look at this. See? Pretty similar, eh? Same kind of tabby cat. Very nice. Oh, do I see another cat coming? This is gonna be awesome. Oh. That's awesome. Okay, I was looking at this example earlier. I think we should try this one. So we're going to see if this is convergent or divergent. Okay, oh, do we have another pet coming in? By the way, if you're on YouTube right now, we got some epic pets being shown on screen. This is awesome. Is that golden retriever? Yeah, that's golden. For sure golden. Oh, he's got us on mute. He's totally muted us out. That's a very nice looking dog. Okay, let's jump into it. So we're gonna do some stuff from 11.5. Okay, so this is section 11.5. Section 11.5. Do you guys know the symbol for section? It's this. It's like an S with a circle in the middle of it. That means section. So I get to do a section 11.5. Okay. And we're going to do, and this is page 513, and this is number 6. Okay? So we're going to test to see if it's convergent or divergent. So is this series convergent or divergent? Convergent or divergent. Okay. So the series is this guy right here. We got some arctan in here, which is kind of fun. So n equals 1 to infinity of arctan of n over n squared plus 1. Interesting. So let's see if we can get to the bottom of this. Now, also in the book, we have a bit of a hint. Okay, so I'll just write the hint out. I don't know if you have the book in front of you or not, but if you don't, oops, I'll tell you what the hint is. And they don't really phrase it as a hint. It's just the question says, use the integral test to determine if it's convergent or divergent. So I'll just say that the hint is use integral test. Okay. Because typically, right, like if I was just to give you a series to evaluate if it converges or diverges, then you wouldn't know right off the hop whether or not you should use like the integral test or the nth term test or the ratio test or what have you. In this case, we're going to use the integral test. So use integral test. Okay. So the idea of the integral test is, if you remember, is we're going to say that, okay, so this thing right here, this thing that I just put in a square, this is going to be equal to an, and we're going to say that f of n is equal to an. So in other words, f of n, I'll write it over here, f of n is equal to arctan of n over n squared plus 1. And I'm hoping that maybe you can kind of see what's going on here. I mean, I want you to take a look at this expression and think, okay, I'm going to use the integral test. If I was to give you this as an integral, are there any particular like neurons that are firing in your brain that are like, oh yeah, I think I know what I would do if this was an integral? Do you know what I'm talking about? Like, because using the integral test, if I didn't tell you that we needed to use the integral test, if you looked at this, you could say, okay, well, if this was an integral, there's some things I could do to it, right? I'm thinking like a u substitution, or sorry, we call it just substitution. I'm thinking we could do a substitution. So what I'm trying to say is that we're gonna have this integral. So we're gonna go from 1 to infinity of arctan of n over n squared plus 1. Oh, and let's turn this into x's because it just looks better as an x. Usually x, like just if you're interested, usually x is used for like continuous variables and n is for like discrete variables like 1, 2, 3, 4. Typically we don't say that n is like 2.5, if you know what I mean. Like n is usually like integers and x is usually used for real numbers. So let's use x. And we want to know, does this converge or diverge? div. Big question mark. Okay, so that's really what we're looking for. So let's start attacking this with some integral stuff. So I'm going to do a substitution. So I'm looking at this, and there's really two things to this. We've got arctan of x, and then we have this is like really arctan of x times 1 over x squared plus 1. Right? Those two things are pretty similar to each other, right? I mean, they're not. I mean, they're not actually that similar, but they have a relationship, right? One is the derivative of the other, right? The derivative of arctan of x is 1 over x squared plus 1. Maybe it's been a while since you've used that fact, but we've done that fact. I think that was one of the first things we did together, right? In the second semester was we proved this using diagrams. I know that because I just finished writing your report cards over the weekend, and I commented on how some of us could do this. Anyway, so let's talk about how to do this. Okay, so I'm gonna say so let u equal arctan of x. Okay, so arctan of x. So that means that du is equal to 1 over x squared plus 1, right? So that means that our integral here is equal to, well, we're still going from 1, I'm going to say that x equals 1 to x equals infinity, because we did change the variable, so we do have to be a little bit careful about the endpoints. And then let's see what happens here. So this is going to be the integral from u du. Okay, so that's good. My cat is kind of sneaking up over here. Oh, and look at that. She knows how to zoom in. Hi, Goose. This is my other cat. I've got 2 cats helping me out. Say hi to everyone. Now say goodbye. Okay. So this is pretty easy to solve, right? So this is going to be well, we've got this is equal to what is it? U. Well, the integral of u du is what? It's u squared. This is equal to u squared over 2, right? And let's convert that back. So I'm kind of saying that this is like I just found the antiderivative of that. And what I'm trying to say is I'm ignoring these endpoints. I'm just finding the antiderivative. And then I'm going to put it back, I'm going to put it back into terms of x. So when I do that, I'm going to have, well, what did I say u was? Arctan of x. So this is arctan of x squared over 2. And we're going from, what was it, 1 to infinity? 1 to infinity? And let's actually change this to like b and take a limit. So we'll do limit as b goes to infinity, right? I guess I could have done that earlier on. I could have written this all as a limit, but as long as you're taking the limit at some point, you're just kind of it's fine. You can take a limit at near the end of the solution as well. It's fine. Okay. So I've got this limit, and so what am I going to do next? So this is going to be, well, let's factor out this 1/2. So this is going to be 1/2 times, well, I've got I guess the limit is the first thing. So I've got the limit as b goes to infinity of not arctan of b, and I'm going to subtract arctan of 1. Okay, arctan of 1. Okay, let's think a little bit about, and then I'm going to close these brackets. So let's think a little bit about this portion right here. So the limit as b goes to infinity of arctan of b, because arctan of 1, that's pretty straightforward. This is just pi over 4, right? It's pi over 4. The limit as b goes to infinity of arctan of b. Let's jump into Desmos for 1 second. I mean, and if you were to be doing this like in an exam or something, you could refer to your calculator for this, right? So let's take a look at arctan of b. Let's look at arctan of b. Okay. So, and let me just steal my keyboard from my computer, put it onto my iPad. Whoops. Okay. Is it and let's not use the variable b. Let's use the variable x because it'll look good on our xy axis. So I'll do y equals arctan of x. Okay, so what's happening here as we tend towards infinity? Okay, well, it looks like it's getting closer and closer to a very specific amount, right? Like, what is this? 1.547. Kind of starting to look a little bit like, what's that, pi over 2, right? I mean, it is pi over 2, but let's just sort of observe that. Well, why is it going towards pi over 2? Well, let's look at the inverse of this. Let's say, okay, well, let's do y equals tan of x, okay? And then go back to the origin. Where are we? Here we go. And remember that this purple guy right here, the arctan of x, is really just the inverse of this principal value of tan of x. This sort of like this middle one right here. I wish you could kind of see what I'm pointing at. Here, maybe I'll do this. It's like, can you see this? I don't know if you can see this, but it's really just the inverse of this first one, right? Where, like, do you remember when we first started talking about like the inverse trigonometric functions? Arctan of x isn't the inverse of all of these. Otherwise this wouldn't be a function. It's just the inverse of this middle one. It's just this, we call this like the principal tan, right? So this middle one right here. So it's the inverse of this line. And okay, so if you look at this graph, like where does this one go towards infinity? Well, pi over 2, right? Because tan of x, let's jump back over to my notebook here. So tan of x goes towards infinity when x is equal, or x gets close to pi over 2. And that's because tan of x is equal to, what is it, sine of x over cos of x? And when x approaches pi over 2, pi over 2, then sine of x approaches, what is it? Hold on a second. Did I get that right? No, it is. What's going on here? Why is this wrong? Pi over 2, because cos of pi over 2 is -1, isn't it? Oh, yeah. So, you know what my problem is? Sometimes I get mixed up with dealing with radians. I'm thinking of the whole thing as pi. You know, that's like tau. Yeah, that would be amazing. If only we could just invent a number that was twice the size of pi. If only that was possible. Yes. Okay. So sine of x would be equal to, in this case, 1. Oops, in red, please, and thank you. 1. And then cos of x gives you 0. And if we're approaching it, then it's kind of like it's approaching like positive 0, if that makes sense. Do you know what I'm saying? Because 0 could be either positive or negative. So this could switch from some positive infinity to negative infinity. I mean, and you can see that too, right? In our graph, like, again, looking right at this video here, or my screen. Where is the origin? Here it is, right? I don't know if this is actually pointless or not, but like right over here. Oh, you know what? I have got my mouse connected, so I'll use my mouse. Look at that. The new version of iPad OS lets you use a mouse. Yeah, this is much better. So like as you approach pi over 2 from the left, you get positive infinity, but if you approach it from the right, you get negative infinity, and that's because over here cos is like -0, right? You're approaching 0 from the left, right? You've got negative values that are very close to 0, so that's why this is negative infinity. So, but we're only concerned with this middle one. So what we're looking for is we're saying, okay, which values of tan between pi over 2 or negative pi over 2 to positive pi over 2 give us infinity? Well, it's positive pi over 2. So this right over here, this is pi over 2. So this answer is, okay, so I've got 1/2 times pi over 2 minus pi over 4, and that is equal to, well, that's going to be what, pi over 4 times 1/2, so this is pi over 8. But ultimately, like, oh yeah, okay, so there's some squareds, square, okay, yeah, so we'd have to square these, right? But ultimately, it doesn't really, like, we could sort of like play around with the squareds here and there, but the point is that it converges, right? So yeah, because we would have arctan of 2. Is that right? Yeah, I think that's fine. Yeah, pi over 2 squared minus pi over 4 squared. So it's not pi over 8. I guess I'm kind of rushing because the whole point is that we don't need to know what, like, we don't really need to know the value of this integral. What we need to know is this integral convergent or divergent? Well, in this case, it is convergent. So I mean, well, we may as well finish what we started. So let's go ahead. This is pi squared over 4 minus pi squared over 16. So yada yada yada. We can solve this if we really want to. What is that going to be? So multiply that by 4. So 4 minus 1 is, so times 3 pi squared over 16. So this is equal to 3 pi squared over 32. Okay. So yeah, I mean, it's, did I make a mistake? No. So this is, I mean, it could be, but it's not necessarily equal to the sum as n equals 1 to infinity of, what was it? Arctan of n over n squared plus 1, right? That was the original one. It's not necessarily equal. In fact, it's almost certainly not equal, but the fact that this converges, so this implies that we have a convergent integral. This implies that we have a convergent series. Okay? Does that make sense? We're not, I mean, the whole point of this is that we don't need to know exactly what the value of that integral is. The real thing that we're looking for is whether or not that integral converges or diverges. If it converges, then the series converges. If it diverges, then the series diverges. Okay? So that's the point of like the whole integral test. So I think it's time for you guys to try one. Let's do. Hold on, I'm just trying to get my keyboard back. Let's do. Do you want to just do the next one? Question 7? I think we can do question 7. Okay, yeah, question 7 is about p-series. Yeah, I want you to do question 7a. Oh, yeah, okay, so there's 7a. So question 7a. Usually this book doesn't have like A, B, C, and D, does it? I thought it was usually just like numbers. Anyway, so I'm going to get you to do question 7a, which says, determine whether the given p-series converges or diverges. So does the given p-series converge or diverge? Okay? Does it converge or diverge? And A is sum from n equals 1 to infinity of, oh, this one's almost too easy. 1 over n cubed. Okay? So you can refer to the p-series test and see what that gets you. Okay? If you had the p test or the p-series test in front of you, you should probably already be done. But you may have to sort of refer back to the p-series test. So go through your notes. Take 2 minutes to go through your notes. Look at the p-series test, and then we'll try a couple other ones. But I'm gonna take this phone call. I've been I know it's kind of inappropriate to take a phone call in the middle of a class, but without getting into too many personal details, there's kind of some stuff I need to deal with. So give me 1 second, and if you finish 7A, then start working through some of the other ones from question 7, because there's a lot of good ones, and it really just illustrates how straightforward the P-series test is. You're really just looking at this exponent, right? In this case, that exponent is 3. Okay, I'll be right back. Okay, yeah, sorry about that. How'd it go? Are we good? Yeah. You got a feeling it converges, and why is that? Is it because 3 is bigger than 1? Nice. Yes, 3 is bigger than 1. So the series converges by the, I'm just gonna write P series test. PST. Not to be confused with GST. Very different. Okay, so the P series does converge. And then same with all of these. So the whole point of these, so like, let's take a look at, I don't know, question E, right? E from question 7. So that would be, the sum n equals 1 to infinity of like 1 over the 4th root of n. Well, the 4th root of n, that's equal to 1 over n to the power of a quarter. And here, like, it's really just converting these into like exponent form, right? Just this is stuff that you probably would have done in grade 10 or something, right? Take a radical and write it as something with a fractional exponent, right? So in this case, a quarter is less than 1, so it diverges. Okay. Okay, so it's just about 2 o'clock, so we've done a couple examples. That's good. Let's see if we can... Let's do... Okay, let's do number 5. Okay, so this is your exit slip. So exit slip. Okay, so here we're going to have number 5 on page 513, and it is to use the integral test, just like question 6 that we did earlier. So we're going to use the integral test to determine convergence or divergence. Okay, now there's a catch. Because I know that the answer is on page, what is it? Page, like I'll tell you, the answer is on page, the back. So probably like page 602, it looks like. No, page 603. It's on page 603. So if you want, you can look at page 603, right? So I'll just say answer on page 603. So it's like a true-false question, right? So you could just look at that. So here's the catch. I want you to tell me what value you get on the integral. So, I mean, yes, absolutely. So number 5 is the sum where n goes from 1 to infinity of n over n squared plus 1. Okay, so essentially we're thinking of this as an integral, right? Now, so the catch is what value did you get? What value did you get when you integrate? Well, then it would be infinity, right? Or maybe negative infinity, right? When you integrate. Okay, so yeah, if it diverges, then tell me if it's positive infinity or negative infinity, right? So that's the catch. And I just had this this sort of epiphany about some things. I'll share them with you. Where is it? Okay, I want to go to Desmos.com. And I also want to go to mathbennett.com. I'm going to start graphing. And I'm going to share with you my computer screen. So give me 1 second here. And what should I do? Okay, so I'm going to sort of help you out a little bit here. So basically what we're going to do is we're going to say, so to test convergence or divergence, we are going to integrate this guy right here, right? We're going to have x over x squared plus 1 dx. Give me this. Okay, what value do you get after you integrate this guy right here? Okay, so that's what I'm going to get. So I want you to tell me yes or no. Does it converge? Or I guess not yes or no, but does it converge or does it diverge? So one of those words should be on the exit slip. And then in addition to that, I'd like you to just tell me what value did you get when you integrated this, the integral from 1 to infinity of x over x squared plus 1. Okay, so that's what I want you to do. Okay, and I'd like to show you this thing that you may find interesting. Here we go. Okay, so here's my computer screen now. We're on Desmos. Desmos is a really, really powerful tool, and it's not just for graphing. There's all sorts of cool things you can do in Desmos, and I just realized this thing the other day. Now, you may have heard of the markup language called LaTeX. So the LaTeX is, I'll just Google it for you real quick. It's spelled like text, but it's actually pronounced LaTeX with like a hard K It's actually kind of like, it's supposed to be a Greek letter chi, like chi. So nerds pronounce it LaTeX, but most people just call it LaTeX. And it's a way for mathematicians and scientists to write out mathematical documents, and it's a great programming sorry, it's not a programming language, it's a markup language. It's a great markup language to learn if you're interested in ever publishing anything, or if you're really like serious about your homework. Then I think by the time I got to grad school, I was doing my assignments in LaTeX, and I did a few in undergrad too. It's just a really professional looking way of writing your mathematical documents. So the cool thing about Desmos is that it automatically is able to determine what the LaTeX version of an expression is. So if we wanted to, like maybe you like have something like the square root of pi. Where's pi? Do we have pi? Or I think I can just write pi and it automatically does that. Pi squared, and then we hit slash to get a fraction over 5x squared. I don't know, something like that. That if I asked you to punch that into this exit slip, you could probably do it, but it would probably, I think just by looking at some of the responses that I've got so far, most people would be like square root of pi, maybe you even spell it like that, squared over, and then that's not really a nice way of writing math. So what you can do is if you go to Desmos and get an expression to look the way it's supposed to look, you can select it, and oh yeah, it doesn't let me you can't right click it, but if you hit Control C, right, copy, and then you paste it into here, this will give you the LaTeX version of the expression. Now I've been writing in LaTeX for about a decade now, so I can read it quite fluently. I know exactly what this means, so you don't have to adjust this or anything. This is perfectly readable to me. So, and just to give you an idea of what this looks like, if I copy this, fraction. So this is saying, okay, so I've got a fraction here, and a fraction has a numerator and a denominator. So you have an open curly bracket and a closed curly bracket. That gives you your numerator. And then the next one, that's your denominator. So your numerator is this thing here. We've got the square root. So the backslash tells the compiler that this is a command or a function, and after that backslash command, there's going to be an input, right? So then the input is followed. So we've got the square root of pi to the power of 2. So if I were to copy this and put it into my fancy dancy compiler, I kind of put this together the other day. So if I just paste it into here and compile it, then you'll be able to see that I can pump out a PDF if it ever decides to finish compiling. Here it is. Ah, there. You saw it? There it is. So there it is. So I was able to compile that, and you get this beautiful looking expression. So if there's ever a time where I give you an exit slip and you're like, I don't know how to write this out. Like, how do you write like a fraction with an exponent and some square roots and stuff? Punch it into Desmos and then just copy and paste it into here, and that's perfectly valid. The natural log of infinity. I think it is. I mean, why don't we take a look? Okay, how do you do infinity? There we go. I don't know. Undefined, I guess. So let's do ln of x. It looks like this is growing. Okay, so basically what it's saying. Okay, so let's look at e to the power of x. Okay, or y equals e to the x. Y equals e to the x. Okay, go back over here. Okay, and we're saying, so which value of x gives us infinity? Well, I think that we would need infinity. Yeah. So I think that the natural log of infinity, or I guess the limit, like the limit as n. How do I do this? I don't know if you can do limits in Desmos, but the limit as n approaches infinity of ln of n, yeah, it would be positive infinity. Yeah, why do you ask? Has that come up? Yeah, where did it come up? Oh, I see. Yeah, no, the natural log of positive infinity, or I mean, that doesn't really make sense to talk about. It's more like the limit as n approaches infinity of the natural log of n would be positive infinity. Yeah. Okay, what am I trying to do here? Screen. There we go. Okay, so there's your exit slip for today. Yeah, if you don't have any other questions, then I'm gonna sign out. And yeah, are we good? Beauty. Okay. Take care, guys. I'll talk to you tomorrow. Bye bye. Oh yeah. Bye, YouTube.